This is Project Explained with Honors Pre-Calculus Chapter 1 review. Now, this review will probably be shorter than all the other chapters just because this chapter was pretty much all Algebra 1, Algebra, and Algebra 2 review. Alright, so now this is an example of what a piecewise function looks like. So as you can see, we have three different functions, and for each function there's a specific domain that we've set, meaning that the function will only look like that function for that domain. So let's graph it. We have, first of all, we have f of x equals x plus 8, and that's in the domain only when x is less than or equal to negative 3. So we can tell that it will be a linear function with a slope of 1. And so since we have a slope of 1 and it's increasing, a trick is just to find out the point when x is negative 3, make our point there, and then we can know it'll just be a for all values left of it, it'll be increasing with the slope of 1. So at negative 3, it'll just be negative 3 plus 5, negative 3 plus 8, which is 5. So we can go over here. Negative 3 comma 5 is right here. Actually, I'll use a different color. Go with red. Negative 3 comma 5. And from there, we can just make a line, a linear line. It's not a perfect line, but hopefully you get the gist. Next up, we know the shape of g of x since it's a parabolic function. Now all we can do is just find its values at negative 3 and 5 and sort of estimate what it'll be looking like. So go here, g of negative 3 equals negative 3 minus 3 equals negative 36. So it'll be like, it'll be out of our range. But at 5, that'll just be 4. Oops, this should be positive. So we know at 5, it'll be at 4. And we also know that the another thing that we can find is vertex. Since the vertex will be between, somewhere between these points. And by looking at the graph, you can see that the vertex will be at the point 3 comma 0. So that's another point that we can graph. And then from there, it'll go somewhere up. So in fact, we can't even see it, but it'll be going somewhere super high up. Next up, we have h of x equals 2, and so for that, that's just going to stay at 2. In fact, something that I wasn't able to do for this one since it goes all the way up, but for this one I can since I can show in the graph. We'll have an open circle here since h of x, it never really is 5, it's just greater than 5. So at 5 we draw an open circle to signify that. And then we can just go here. And as you can see here, it's a closed circle. There is no open circle since this is for f of x, and f of x is indeed negative 3 at one point. So this has been the Unit 1 review. It was pretty short, but you can expect all the other ones to be more in depth, as we start to get into some new concepts in these ones. Thank you. One last topic from chapter 1 I wanted to go over, and even though we didn't do it in algebra, it definitely can become a little challenging. So say I have functions f of x, which is equivalent to 2x minus 6, and g of x, which is x squared plus 7x plus 6. And what we're going to do here is composing functions. And so what that basically means, the output of one function becomes the input of one function. And so typically you'll see something like this. G of f of 2, which basically we're going to find f of 2 and plug in that value into g of x. So let me show you how we do it. So we'll take f of 2 first, and we'll find out that f of 2 is just 2 times 2 minus 6, which is negative 2. Now I'm going to take that value, plug that into g of x. So now I'm going to do g of negative 2, which is negative 2 squared plus 7 times negative 2 plus 6, which is 4 minus 14 plus 6, which is negative 4. However, a lot more commonly you'll see something like this, f of g of x. And so in that, we want to take g of x and plug that whole thing into f of x. And so the way that works is like this. Since g of x we know is x squared plus 7x plus 6, we can take all of that and plug it into f of x, which is just 2x minus 6. So by plugging in this into here, we're going to end up with f of x squared plus 7x plus 6. There's going to be 2 times that, x squared plus 7x plus 6 minus 6 over here. So that gives us 2x squared plus 14x plus 12 minus 6, which is just 2x squared plus 14x plus 6. This is Honors Pre-Calculus Chapter 2 review. So let's get started. So one of the concepts reviewed in one of the concepts of Chapter 2 was characteristics of a function. These characteristics include if it's increasing, decreasing, its minimum and maximums, and its concavity. So if we were to take a look at a graph of a function right here, the function is increasing in some parts and decreasing in other parts. So if we were to look in this green area selected, we can see that from it's increasing as from here to here, from these two endpoints. Like let's say we would call this one A and this one B. For all values where A is less than X, which is less than B, f of A is going to be less than f of B, so it's increasing. And so similarly, or intuitively, for decreasing it's the opposite. If you're going down, then the function is decreasing. So for example, in this range circle, the function is decreasing. Now, another point went over was minimum and maximum points. So this point right here, this point is a local max. And I'll circle all local max in yellow. A local max is just, it's the largest value of function within a small interval. So from in this interval, you have a local max here up until the next local max over here and over here. However, this point also happens to be a global max. A global max is just a max point overall for a function. Now, Similarly, as we have local and global maximums, we also have minimums. So here's a local minimum, but this point also happens to be the global minimum, as there's no other point so far which is, so this is also the global minimum. However, there are other local minimums, such as this point right here. Now, concavity of a function is, in a way you can think about it, is like if you could trace like a cup or like a U-shaped curve right side up. So if you were to look at this portion of the function, it is a concave up, and if you were to look at this portion, it is, I mean, it's not a great drawing, but it is supposed to be concave down. Similarly, this part is also concave down, because you can trace an upside down cup or an upside down U, and this portion is concave up. And another concept which was discussed in chapter 2 was even or odd functions. So a function is even if, say, function f of x is even if I were to input in negative x, I would still get f of x. However, a function is going to be odd if I were to plug in if in f of negative x, I get negative f of x. So let's do a quick practice problem for this. So say I have the function f of x equals 3x cubed minus x. Now we're going to plug in f of negative x, because that's how you tell. You always want to plug in this negative x as a whole and not values, because there could be some values where it turns out to be like f of, say, negative 2 and equals something, and f of 2 equals the opposite of that. But just to be safe, you want to plug in negative x. And so if I plug in negative x here, I get 3 times negative x cubed minus negative x, which then becomes 3 times negative x cubed here plus x, and this is just negative 3x cubed. I have x here. And so we see that when I plugged in f of negative x, I actually got negative of f of x. Because if I look at f of x and then a negative of that, multiply this whole thing by negative 1, this function here by negative 1, I would have gotten this thing. And so while these are some of the ideas discussed in chapter 2, the main concept of chapter 2 revolved around the unit circle. So the unit circle introduces like a new set of measuring angles. As before, we use degrees, but the unit circle we use radians. And so the unit circle is actually based off of a real circle. Like the points, the sine and cosine functions, which we'll get to later, they're called circular functions because they are equal to points along the arc of a circle. So if I were to have a right triangle here, hold on. I would have a right triangle here. with, say, r as in the radius. Here's angle theta. Here is x. And here's y. Tan of that would give me y over x. Sine of that would give me y over r. And then cosine of that would give me x over r. Another thing to now we can actually, if you have the unit circle memorized, it's a good idea to, even if you don't have to have it memorized, just kind of be able to recall it, because a lot of the problems, that's going to be helpful. But nonetheless, if you can't remember, or you can't help, or can't figure out where a point on the unit circle would be, something you can do is, if you have the radian measure and you multiply the radian measure by 180 degrees and then divide that by pi, you'll get the answer in degrees. And so that might be able to help you place or find or figure out where the angle is. So let's do a couple of these problems, and then we'll also go over how to graph a sine function. So say I have the problem 4 sine squared theta minus 3 equals 0. First thing, since I want to solve for theta, so I'll add 3 to both sides. That'll just give me with 3. Then I'll divide both sides by 4. So I got sine square theta equals 3/4. Then I'll take the square root of both sides, just so I can end up with sine theta and not sine square theta. And so when I take the square root, I get plus or minus root 3 divided by 2. And then since we got two angles, I guess first a good something that helps me a lot is graphing a unit, or just making a quick sketch of a unit circle and to find where that would be. So if I were to go, whoops. It's not a great circle, but it's still alright. So knowing the unit circle, I would know that this value is at about here and here. So now I gotta find out the sine of these 4 points. 1, 2, 3, and 4. And so since this is asking for sine, this is actually going to include all possible values of sine, and it's not, we don't have a restricted domain, so it doesn't say inverse sine of something. Even though in the next step we are going to take inverse sine, since in the problem it didn't say inverse sine, we're going to assume this is for all possible values. So first off, we're gonna do something that you could, the easiest way, now there is some overlap between these answers, but just to make sure that you got it, you can just say pi over 3 plus 2 pi n 2 pi over 3 plus 2 pi n. Since these are where this angle, this over here is the angle pi over 3. This right here is going to be 2 pi over 3. This one is 4 pi over 3, and this one is 5 pi over 3. So while I could continue just for saying plus 2 pi n for all of these angles, like that, and then another one for 5 pi. Another way to keep it simple, again, this answer would be correct, but you could simplify and realize that since pi over 3 plus pi gives you 4 pi over 3, and 2 pi over 3 plus pi gives you 5 pi over 3, you could simplify this just to be pi over 3 plus pi n, since now this does include 4 pi over 3. And similarly, you could do 2 pi over 3 plus pi n. Now let's do another problem. So say I have 2 cosine theta minus 1 equals 0. Again, first things I'm gonna add 1 to both sides. So that gives me 1. Then I'll divide by 2 equals 1/2. So I want to find when arc cosine of theta gives me 1/2. I want to find when cosine of theta is 1/2. So again, if I were to make a quick sketch, it's not a great sketch, but give us a rough estimate. And so we realize that cosine theta, so first of all, since it's positive, cosine is positive in quadrants 1 and 4. And so that'll be looking at like about here. And so knowing the unit circle, this will be the angle pi over 3, and this will be at 5 pi over 3. And so that's like that. Then we can just create our equations, plus 2 pi n and plus 2 pi n. So knowing when cosine and sine are positive would be a really big advantage. Also, another thing to know is that when, for inverse of these, what quadrants is a graph for the inverse of a sine graph or the inverse of a cosine graph? Because when you're solving, sometimes you're gonna have a limited domain from 0 to 2 pi. If its fair just gives you inverse sine of something, then you're gonna have a limited domain. So for that, inverse sine is only valid in quadrants 1 and 3. 1 and 4. Inverse cosine only works in quadrants 2 and 3. And then inverse tan, which is pretty uncommon to see that, but if you were to see it, that's only in quadrants 1 and 4. And so that wraps up. One final thing before we wrap up is we'll do an example of graphing sine. So let's say I have, here's my axes. Alright, so let's say I have to graph, I'm given the equation, to say y equals -2 sine x minus pi plus 2. So how would I graph it? Well, the first thing is we see that our midline is at +2. and that our amplitude is 2. So I'll just make this this yellow line that I'm about to draw, that can be representative of where the point y equals 2 would be. And that gives us a good knowledge. Also, another thing that we want to do is we want to label our axes, our x-axis. So since the period is still, since the b value is only 1, meaning there is no horizontal compression, our period will still be 2 pi. So I can make a tick mark here at pi over 2 pi 3 pi over 2 pi and then at 5 pi. So actually I'm going to extend this here, and you'll see why in a sec. And then I just make some here, so we got negative pi over 2 negative pi negative 3 pi over 2. Alright, so first off we see that's x minus pi, meaning it's gonna be shifted by pi units to the right. So we're gonna just we have a point here. Also, since our amplitude is 2 but it's negative, that means that we're gonna go down 2 since it's negative, then later we'll go up by 2 since that's what the amplitude tells us. So I can make a point here at 4, make a point here at negative 2, point here at negative 4. So now that I have a point here, this will be negative at the next interval, which is basically every period divided by 4. That's one way to think about it. Now we're gonna actually there's a different color. So I'll be up here. Then I'm gonna come down here. Actually no, I'm gonna come down here to 0, go down 2. Then I'm gonna go up 2 again. I'm gonna go up 2 here. And I don't have a marker for 3 pi, so I guess I'll make one, but that'll be where I'm gonna be at next. And then since it's usually recommended to graph 1.5 cycles, I know that I'm gonna be coming from up here. Whoops, different color. I'm gonna be coming from up here and going here. So now I'll zoom in a little bit and then look something like this. Go up here, go down here, and then we know that it'll go like that. And so that's the review of chapter 2. Thanks for watching. Alright, so now this is Honors Pre-Calculus chapter 3 review. So one of the things that we'll go over is partial fraction decomposition, and this is how it works. So say I got this going on, 8x plus 7 divided by x plus 2 times x minus 1. And so since I know that when I added something over x plus 2 plus something over x minus 1. Now the next thing I want to do is I want to multiply the whole thing of by the denominator of this. So I want to multiply the whole thing by this. So when I do that, I'm going to be left with 8x plus 7 equals, since I multiply multiply this whole thing over here, when I multiply this by x plus 2 times x minus 1, the x plus 2 are going to cancel out, and I'll get a times x minus 1. And similarly, when I do the thing over here for this section, I'll multiply it by the x minus 1s are going to cancel out, so I'll be left with xb times x plus 2. Now to find a and b, what you're going to use is basically going to try to eliminate both of these variables. So first off, let's say x equals 1. Then what's going to happen? We're going to get 8 times 1 plus 7 equals a times 1 minus 1. That's just 0. So this is just nothing because we have 0a plus b times 1 plus 2, which is 3. So then we get 15 equals 3b, b equals 5. Then I'll do the same thing but for the other one. So in this one, to make the b this side 0, x will have to be negative 2. So if x equals negative 2, then I'm going to be left with 8 times negative 2 plus 7, which equals a times negative 3, since negative 1 minus 2. So negative 3 plus b times 0, which we can cancel out. So now we get negative 9 equals negative 3a. Divide both sides by negative 3 and we get a equals 3. So now we're not done yet, but we almost are. So now we can just say as our final answer, 3, since that was our value for a, times x plus 2, since we have to substitute it back in, plus, what was it, 5 for our value of b. 5 times x minus 1 equals 8x plus 7 divided by x plus 2 times x minus 1. Yeah. Another thing that was covered in chapter 3 was variation. So direct variation. So in all of these, first of all, k is a constant, and it does not equal 0. That's something that we can assume. So in direct variation, is when y varies directly as x, and so with k as our constant, it'll look something like this. As when x increases, y will increase, and when x decreases, actually that doesn't. If k is our constant, so depending on k, but yeah, y depends on x. And so if it's joint, that means that y depends on two variables, such as say we have y equals kz times kzx, in which k is still the constant, but now the value of y depends on z and x. Now, as both these have been multiplication, but if we look at an inverse variation, or that's when y varies inversely as x. So an example of that could be y equals k divided by x. Again, in which k is a constant. So let's look at like a quick sample problem. So with this in mind, say in a certain situation, y varies directly as x to the fifth inversely as the root of x. So then we're going to end up with something looking like x to the fifth here, but then actually no, not root x. Let's say we have root z. So now we'll be left with over root z. And so while these were both covered in chapter 3, the main thing chapter 3 was about was area under the curve. And so we'll get to that, but before we get to that, something to just to keep in mind are what intervals are. So intervals, in intervals we use subscript notation, and they're used when an interval is split into multiple parts to represent various values, like consecutive values. So say from the from here 2 to 4, we want to divide into 4 equal pieces. So that'll look something like this. So say we have 2 here, 4 here, that means 3 is going to be somewhere in the middle. And the way we find out how many, since we have how many or what the width of is going to, or the size of each piece is going to be, what we do is we do the big value. So that'll, in this case, that'll be like 4 minus 2 divided by how many pieces? That's 4, so that's 2 divided by 4, which is 0.5. So that means we're going to go by halves here. So over here we might have 2.5, and then over here it'll be 3.5. Now, this, however, in subscript notation, this would be written as something like x of 0, x of 1, x of 2, x of 3 here, and x of 4. So with that in mind, this is how we do figure out left endpoint or right endpoint, or the area under curve using left endpoint rectangle approximation method or right endpoint approximation method. So in that, the two things that we like to use to figure this out are the change of x, which is the width of each rectangle, which I'll get to in a sec, and f of x of k, which determines the height of a rectangle. So if I were to use the left endpoint approximation method called LRAM, if I have let's say I have a graph of a line right here. In left endpoint method, so and let's say I want to go in from the interval here to here. In left endpoint method, and so say I want to do like 4 rectangles, right? And I figured that out already. So 4 rectangles. These aren't super evenly spaced, but it's fine. In the left endpoint method, I'm going to go from this interval's left point here, from where this touches. Another rectangle is going to be over here. when this touches, and I'm going to make another line over here when this touches, and another line here when this touches. Now since this is the left endpoint, I'm going to use the left endpoint of this, and then I'm going to make a rectangle here, go here, go here. And so now I have these 3 rectangles. Actually, I said I wanted 4, didn't I? So then I'll probably have to make, well, I guess I'll extend the line first of all. Then I'll go and so now I have my 4 rectangles, which will be like this. And I'll be basically I found the area of each rectangle and added up. However, in the right endpoint approximation method, or rectangle approximation method, while it's similar, scenario, let's say I got this here. And I have the same, I'm making 4 rectangles. I'm actually going to start, so I'll make the, I'm going to start from here when this connects. I'm going to go here when this intersects, going to go here and here, like that. And then I'm going to go horizontally and then down to the previous mark, and then horizontally, and then down, and then horizontally, and then down like that, horizontally, and then down. So as you can see, when the function is increasing, using LRAM, it's actually an underestimation. The area is going to be an underestimation, and using RM, it'll be an overestimation. However, when the function is going to be decreasing, it'll actually be the opposite. So in RM, we're finding the area of all of these rectangles. So when I'm using LRAM, I'm going to use a sigma notation to find, because in sigma, this means the sum of. So I'm going to use a sigma notation, which will look something like, and I'll do an example problem soon. But my sigma notation, since I'm going to start at the 0, 1, as you saw here, since in x of 0, in LRAM based on going from x of 0 to x of 3, and in RM I would be going from x of 1 to x of 4. So from in LRAM, I'm going to k of 0 to 1 less than the total, and I'll be going f of the function of the graph. So like say this is a function f of x, and this is f of x, the white line, f of x of k times the width. But for RM over here, it'll be similar except n, and it'll be k. I'm going to start off at 1 since it's RM. If I look at this graph, I would be trying to find the area, kind of using from x of 1 to x of 4, but in LRAM I'm at x of 0 to x of 3. So here I am, I'll be at n k equals 1, and then the rest of it is going to be the same, f of x of k times the width of each rectangle. And we'll get to what I'm talking about in a sec. So say I have the equation, the function f of x, which is 1/4 x squared plus 2, and I want 5 rectangles from the interval 1 to 6, and I'm told that I have to use LRAM. So first I'm going to calculate the width. And the width I do from the maximum x value, subtract to the minimum x value, and divide that by total number of rectangles. And so in this case I get 1 for that, which is pretty good. So that means that the width of each rectangle is 1. Now, since I'm using LRAM, and since so I'm starting off at 1, that means x of 0 is going to be 1. And my equation for x of k, since my width is 1, it'll be 1 times k plus my y-intercept, which is 1. And since this is 1 times k, we can get rid of this, and it'll just be k plus 1. So now I'm going to go back to using my sigma notation. And so k, since it's LRAM, k starts off at 0. We go to since we have 5 rectangles, so we do 5 minus 1 here, which is 4. Then I'm going to plug in the equation f of x, except for x, I'm going to plug in x of k. That's how I get ko down here. So it'll be, since the original equation is 1/4 x squared, well, my equation for k is k plus 1, or my equation for x of k is k plus 1. I'm going to plug in k plus 1. And the rest of it is going to be the same. So you have squared plus 2. And then multiplied by my width, which happens to be 1. So I don't really have to do that. But when I put this in my calculator in sigma notation, I should get 23.75 units squared for my area. And yeah, that covers up chapter 3 review of HPC.
So now we'll be moving on to chapter 5 of Honors Pre-Calculus, which covers exponentials and logarithms. So just to review, I want to start by looking at the graph f of x equals a times b to the power of x minus h plus k. Let me just fix that real quick. X minus h and then plus k. So essentially this is the parent, so this right here would just be the parent exponential graph, and something like, the graph would essentially look something like this. If I just sketch it real quick, it'll look something like that. And we can note that the y-intercept is always going to be at 0, a, and that in this function, what these transformations are here is that this h is going to be our horizontal shift, this k will be our vertical shift, which also happens to be our horizontal asymptote. So this will also be our horizontal asymptote. So in the case of this function, we can basically write this as plus 0. So we essentially know that our x-axis also serves as our horizontal asymptote. So so just to go over what we've covered so far, 0, a is the y-intercept, and then we know that h is the horizontal shift and k is the vertical shift, and this a value will be our vertical stretch. So essentially, if b is greater than 1, then we know that our graph is going to be looking something like this. It'll be increasing, essentially. But if we say that, let's just say that b is between, so when b is between 0 and 1, so b is between 0 and 1, we know that our graph will be looking something more like this. And that's, so let's just say, for example, f of x equals 1/3 to the power of x. That's essentially what our graph would look like. It would be decreasing here. And just to go over some of the basic exponent properties, if we forgot them, x times x to the m times x to the n, that becomes x to the power of m times n. m plus n, and then x over m, or xm over x to the power of n will essentially become x to the power of m minus n. And then obviously x to the power of 0 is always equal to 1 when x is not equal to 0. And then x to the power of negative n is equal to 1 over x to the n. And then lastly, x to the power of m over n will simply be equal to x to the m, the nth root of that will be that's what x to the power of m over n equals. So that's just a quick review of our laws of exponents, as well as the parent graph of f of x equals a times b to the power of x. And then the next concept within exponentials I want to go over is our interest problems. And there's two main formulas that we want to remember. The first one is a, which is our amount, is equal to the principal p times 1 plus r over n to the power of n times t. And essentially what, if we just write this out over here, we know that a is equal to the amount, and then p is equal to our principal, and the principal is essentially just how much we start with. And then r is going to be our rate, so what is our interest rate essentially. So for example, an 8% interest, the rate you would just write that is 0.08, and then finally n is equal to the number of times we compound per year. So let's say that we are compounding quarterly, that means n is equal to 4, because we compound 4 times within a year. And then t is simply time, and then this is usually in years. And then the second essentially formula that we want to know is a is equal to p times e to the power of rt. And then these these variables here, here, and here are all the same, except for that this is the number e, which is basically approximately, we can say it's approximately 2.72. And the main difference between this this formula here and this formula here is that this is discrete. This is over a discrete amount of time. So when we say discrete, we could say that we're compounding interest for 3 years, something like that, a fixed time period. But on the other hand, this right here, well, this is continuous interest, which means we're essentially compounding, just compounding forever. So anytime you see the word continuous in a problem, you immediately want to refer to this formula here, not the one above. So now that we've gone over our law of exponents, we probably want to look at a problem that we may see, like a problem that we may see on a test or something. So let's say that f of x, let's say they give us the function f of x is equal to 3 times 4 to the power of x plus 2. And what they want us to do is rewrite this in the form f of x equals a times b to the power of x. So essentially, using our knowledge of exponent laws, we will be able to convert from this form into just this form over here, where there's nothing in the exponent except just that x. So essentially how I'm going to do this is, if I just go over here, I can write this as 3 times 4 to the power of 2 times 4 to the power of x. And if we remember that the reason why I'm able to do this is I'm referring to the exponent law, x times x of m, or x to the power of m, times x to the power of n is equal to x m plus n. So essentially that's the law I'm using here. And then if we just simplify this over here, well, 4 squared is 16, 16 times 3 is 48, so we know that we can rewrite this as 48 times 4 to the power of x. and that would be our answer. So now that we've gone over everything about exponentials, we want to talk about logs now. So essentially, let's say I have the exponential b to the power of y is equal to x. Well, if we know if b is greater than 0 and x is greater than 0, then essentially what we can do is we can rewrite this right here as this can be rewritten as y is equal to log base b to the power of x. And that's essentially how we rewrite from our exponentials to our logarithms. And then there's also something called, just as quick review, something called natural log. And the natural log is essentially a logarithm with the base e. So basically how we write this is we write this as ln. So if I say ln of x, that would be just equal to the natural log, so log, and then we have to remember we're using the base e to the power of x. So that's essentially how we write our natural log. And then if we go to our log properties, well, we know that log b to the power of 1 is always going to be equal to 0, and that log b to the power of b is going to be equal to 1, because we know that these will cancel out, and that also log b to the power of b to the x, like written like this, well, we know that these b's will cancel out, so essentially this is just going to be equal to, this will just be equal to x. And then our product property, so log b, let's say x and y, xy, well, that can be rewritten as log b to the power of x plus log b to the power of y. And then another property is we can say that our quotient property would be like log b to the power of x minus log b to the power of y. That's just equal to log b x over y. And then we also have our power property, so we can say that if we have log b, let's say to the x, and that's the m, well, we can just rewrite this as m times log b to the power of x. So those are our log properties. And also something very useful to know is if I'm just going to get rid of this now since we've gone over this. Another useful thing that we may need to use on a test or something is something known as the change of base formula. So change of base formula. And let's say I have the log 2, 3. And let's say I want to rewrite this with, let's say I want to rewrite this as the, I'll say to the base 10. So I want to do base 10. All I have to do is do log, and then this would be 10 to the third over log 10 to the second. So essentially the formula that you want to follow for change of base would be log AB is equal to log CB over log CA. And then that's our change of base formula. So now that we've gone over our log properties and stuff, we can start to look at the graph of the parent graph of log. So essentially if I just draw an axis here, the first thing I'm going to do is I'm going to draw the parent graph for the inverse of our logarithm function, which would essentially be our exponential function, which is y equals ab to the power of x. So I'll just draw it like this. And essentially we know that for inverses, it's going to just be reflected over the line y is equal to x. So our log graph is going to just look something like this. So essentially it's just a reflection. It's just a reflection of the line y is equal to x. And so let's say our graph f of x is equal to log x. Remember, if I'm not writing a base here, we're assuming that this is base 10. And then the x-intercept for this graph is going to be 1 comma 0, and we know this because, well, if we set f of x, which is essentially y, to 0 equals log x, we're essentially saying, well, 10 to the power of 0 is equal to x, and we know anything to the power of 0 is equal to 1, so x is equal to 1. So that's how we know that our x-intercept is 1 comma 0. For the y-intercept, there is no y-intercept, so none. And then we can look at we have no horizontal asymptote. So essentially our range is all real numbers, but our domain is restricted because we do have a vertical asymptote. We have a vertical asymptote at sorry about that. We have a vertical asymptote as x is equal to 0. So on this graph, we would just have a vertical asymptote going down like that, and that would just be x is equal to 0. And essentially, you just need to remember for the log graph, it is the inverse of the graph f of x is equal to abx. So yeah, that's all there is to know basically about the log graph. So now moving into chapter 6 of honors pre-calculus, we're going to be going into triangles and solving triangles as well as vectors. So just for some review as we start off with our triangles, so just some review, we want to remember that sine theta is obviously opposite over hypotenuse. Opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, and tan theta is equal to opposite over adjacent. So now that we have our basic right triangle trigonometry done, we can move into some of our laws. So there's obviously law of sines. So law of sines, and essentially what that means is within a given triangle, the sine of one angle over its corresponding side length is equal to the sine of another angle over that angle's corresponding side length. And then obviously you have the law of cosines, which is again c squared equals a squared plus b squared minus 2ab cosine c. And then for this law, just make sure that obviously the side length here is corresponding to the cosine of the angle over here. And essentially we will be applying all of this in order to solve triangles. So part of solving triangles is obviously dealing with the ambiguous case of law of sines. So ambiguous case of law of sines. And obviously this case occurs when we are given, so we're going to be given SSA. And I'm not going to exactly explain how the case works, more I'm just going to go through a practice problem and just show how the case can be applied. So let's say I draw the triangle, triangle ABC. So I'm going to draw a triangle ABC just like this, and we'll say that let's just say this is A, this is B, and that this is C. And we'll say that this side length over here, which is A, is 6, and we'll say the side length B is 8, and we will say that this is 35 degrees. So essentially, in order to solve the triangle, what we'd have to do is we would have to find this angle over here. Once we get that, we can use the triangle sum theorem, knowing that all angles add up to 180. We would be able to find this angle, and then using law of sines again, we would be able to find this side length C over here. So essentially, in order to solve this triangle, that's what you would have to do. But for now, I'm just going to really go into the ambiguous case of law of sines and determine how many triangles can be formed here. So first, let's find this angle over here. So this angle right here, so we'll call this angle theta. So we'll say that sine theta, or this would be b technically, I'll just say theta. Sine theta over 8 is equal to sine 35 over 6. And if you get your calculator and plug that in, that should just be, so first you'll do 8 times sine 35, and then divide that number by 6, and then do arc sine of that, and that should give you 49.886 degrees. So we're saying theta is 49.886 degrees. So now that we've found that angle, we know that basically what we'll have to do now is we've found this angle. So to determine if there can be two triangles, all we'll do is do 180 minus theta, and we'll see if this violates the triangle sum theorem. So essentially, this angle is given. So this angle is not being adjusted at all. So we'll do 180 minus 49.886. So 180 minus 49.886, and that is 130. So 130 plus our given angle. So remember, this angle here does not change. It's our given angle. So we'll do 130 plus 35, and that is equal to 165, which is less than 180, meaning that we'll have two possible triangles in this case. Now let's just go into a dot product practice problem. So we're going to be using dot product here to find the angle between two vectors. So the two vectors we'll be doing are vector u, which has a component form of 2, 3, and vector v, which has a component form, here, let me rewrite that, vector v, which has a component form of 5, 6. Oops. 5, 6, there we go. So, as we said before, if we take the dot product of these two, which if we do that, it'll be 2 times 5 plus 6 times 3, which will be equal to 28. So we know the dot product is 28, and the dot product is equal to, the magnitudes of both. So the magnitude of u times the magnitude of v, and then cosine, and then the angle in between u and v. So going back here, we know if we find the magnitude of both of these vectors, the first one, so 3 squared plus 4 squared is 13, so the magnitude of u will be root 13, and then we'll multiply that by the magnitude of v, which will be 5 squared plus 6 squared, so that would be 61, so root 61, and then times cosine theta. So if I just rearrange this, essentially I'm getting 28 over root 13 times root 61 is equal to cosine theta, which means that theta is just equal to cosine inverse 28 over root 13 times root 61. And if I just plug this into the calculator real quick, so let me just plug this in, it'll be 28 over root 13 times root 61, and that will give me 6.116 degrees. So that's essentially how we can find the angle between two vectors given their component forms. So now we'll be going into a problem where we get to apply our vectors concepts in a word problem sort of thing. So it says if a force of 30 newtons pulls on an object at an angle of 25 degrees above due west, and another force of 35 newtons pulls the object at an angle of 55 degrees below due east, find the magnitude and direction of the resultant force. So we'll first start with, okay, we have our force. Our first force is 30 newtons and angle of 25 degrees above due west. And then we have 35 newtons at an angle of 55 degrees below due east. So if we draw this on a plane, essentially what we're seeing here is we're seeing that our first force is, so this is west, this would be east, this would be north, and this would be south. Essentially what we're seeing is that our first force is 25 degrees above due west. So here's west, so we're just going to go 25 degrees above that. And that is our first force. That angle right there, that is 25 degrees. And then this magnitude here is 30 newtons. And our second force, which is right here, is 55 degrees below due east. So due east is right here. We just go 55 degrees below that, like something like that. This is 55 degrees. The magnitude of this vector over here is 35 newtons. So just go 35 newtons. And essentially to find the resultant, so the magnitude and direction of the resultant force, how I usually like to do these problems is I like to just go with the components and then just add them. I just find it a lot easier than doing just a lot easier and faster than just doing the triangle trigonometry. But you could do it either way. I'm going to do it with the components. So to find the component of our, we'll just say to find, we'll start with our first vector over here. So that will essentially be our magnitude times our vector angle. And remember, we're going from the positive x-axis here. So technically what we're doing is we're going 180 and then minus 25. So our vector angle in this case is not 25 degrees, but we're going from our positive x-axis. So our vector angle for our first angle would essentially be this right here. That would be our angle right there. And that's just essentially 180 minus 25. So that'd be 155. So I'll do 30 times cosine 155, and then comma, I'll do, this will be 30 times sine 155. So that's the component form for our first vector. Our second vector, well, we have a magnitude of 35 newtons. So 35 times cosine. Now remember, we need to be careful here. Our vector angle goes from our positive x-axis. So we're essentially going here. We're going all the way around to here. So essentially we're going 360 minus 55. So our vector angle in this case will be 305 degrees. So 35 times cosine 305, and then 35 times sine 305. So now that we have our two components, all I'm really going to do is I'm just going to add these up. So if I just do the math here real quick, I'm going to just do this on my calculator. This might take some time, but 35 times. So I would suggest that you just follow along and do this to make sure you got it all right. Okay, yeah, so I've got my horizontal and vertical components now. So once I've added these horizontal components up, I ended up getting minus 7.1 0.114. And then for these vertical components, I ended up getting minus 15.991. So these are our horizontal and vertical components. Now all this is asking is just like we just want to find the direction and the magnitude. So that's fairly simple. We can just, for our magnitude, so we'll just say that this resultant vector is v. For the magnitude of v, we'll just take root negative 7.114 squared plus negative 15.991 squared all over square root. And then if I calculate that real quick, we will end up getting 17.502 newtons. That is our magnitude of the resultant vector. Now remember, to find our direction, what we're going to do is we're going to take the arctan of our horizontal or our vertical component over our horizontal component, so 15.991 over negative 7.114. And if I just plug that into a calculator, we'll say tan inverse negative 15.991 over negative 7.114. And we get a vector angle of 66.017 degrees. So that's how we find the magnitude and direction of the resultant force for this problem.